Rockets are cool. They're used for many things, including sending astronauts to the moon, delivering satellites into orbit, and weapon systems.
The main way that rockets work is by creating a chemical reaction that releases energy. This is very different from how airplanes work, which use jet engines to take in air to create a chemical reaction. You obviously cannot do this in space because there is no air, so rockets basically have to bring their own air by carrying around their fuel and oxidizer with them. If you don't know what fuel and oxidizer means, don't worry, we will explain that very soon. You put these two together to make a chemical reaction and move the rocket forward.
Chemical rockets need two things. First, a fuel source to be burned, and second, an oxidizer that reacts with the fuel. Together, these form the rocket propellant. There are two main types of chemical rockets, liquid and solid. Liquid rocket engines use a liquid propellant where the fuel and oxidizer are stored in separate tanks. On the other hand, solid rockets use a solid propellant, which is made of the fuel and oxidizer, but preloaded in a solid form.
Most rockets use liquid rocket engines. There are a lot of reasons for this, but most of it comes down to being able to turn off the engine, as well as liquid rockets having higher exhaust velocities. With a solid rocket, the oxidizer and the fuel are mixed together at the start. After a solid rocket's engine is turned on, there's nothing you can really do to stop it. However, solid rocket fuel can be stored for longer periods of time, and there is less risk of accidental explosion because solid rockets are simpler.
When the chemical reaction happens, there is motion in the opposite direction. This is called acceleration, and it is part of Newton's third law. This important law of nature states that for every action, there is an equal and opposite reaction. An example of this is when you are walking across a room. The reason that you are not falling through the floor is because the force of your weight on the floor is balanced out by the equal and opposite force of the floor's strength. This is called the normal force. There is a limit to how much energy or acceleration is provided by chemical rockets. This is why it is very important to decide how we can best use the limited propellant that we have. It's the same as if your mom gave you $50, generous mom. You wouldn't just want to use it willy-nilly. You want to plan so you can make the most out of it.
This is where the rocket equation comes in. The rocket equation, seen here, helps us calculate the velocity of our rocket at the end of its voyage, after it has been accelerating for some amount of time. As we can see, the final velocity of a rocket, delta V, depends on VE, which is the exhaust velocity. The exhaust velocity is a finite value that depends on what types of fuel we are using. Some types of rocket fuels, such as hydrogen and oxygen reactions, have exhaust velocities of 2.5 kilometers per second, whereas weaker rockets move slower at a maximum exhaust velocity of 2 kilometers per second. Fun fact, hydrogen and oxygen is actually what NASA uses to launch their rockets.
The ln in the equation is a fancy operation that we won't get into, but it is called the natural logarithm function, also called the natural log. What we are doing in this equation is finding the natural log of the ratio of the initial mass of the rocket to the final mass of the rocket. The larger this value is, the larger the delta V, which is the final velocity in this equation.
Now, we'll work through an example of how the rocket equation works. Suppose that we have a rocket named Roger X. Roger X is powered by hydrogen and oxygen, which means that it has an exhaust velocity of 2.5 kilometers per second. Our rocket's initial mass at launch is 15,000 kilograms, and the final mass is 2,000 kilograms. The initial weight that we had minus, let's say, 13,000 kilograms of propellant that we use is 15,000 kilograms minus 13,000 kilograms, which equals 2,000 kilograms. This is our final mass for our rocket after it has used all of its propellant.
By plugging these values into the rocket equation, we can figure out that the change in velocity is about 5.04 kilometers per second. If we were to change some of the variables, this value would be different. Interestingly enough, we can actually do this strategically by splitting up our tank and throwing it off our rocket to avoid having extra weight.
Have you ever wondered how scientists figure out the most efficient way to use its energy? Now, throughout our rocket's journey, we are carrying the mass of the tank, which is weighing down the rocket. So, scientists have discovered that if we use a process called rocket staging, which splits up the propellant tank into several smaller tanks, we can maximize our final velocity. By splitting our tank in half, we are able to get rid of half of the mass from the propellant tank in the middle of our journey. This uses the same rocket equation that we talked about before.
If this sounds complicated, don't worry. We'll break it down for you right now. Remember Roger X? Roger X from the previous problem is an example of a one-stage rocket because we carried around the tank with us the whole time. Now, what if Roger X used rocket staging to increase its final velocity? We said that Roger X's total mass was 15,000 kilograms.
Let's see what the final velocity would be if we used rocket staging. Notice that we got 5.54 kilometers per second, which is 0.5 kilometers per second larger than Roger X, using the same amount of rocket propellant without using this cool rocket staging technique. An additional 0.5 kilometers per second may not seem like a lot, but it is nearly a 10% increase in the final velocity, whilst using the same amount of energy, just in a smarter way.
Let's review what we learned. In this video, we learned that rockets rely on chemical reactions to get them into orbit or move them through space. The rocket equation is a useful tool we can use to calculate the change in velocity, aka the final velocity, of a rocket at the end of its voyage. We also learned about what rocket staging is and why it is so significant for going faster by breaking up one large propellant tank into several small